In the previous two videos on circular motion, I covered theory and then I did some examples. And in this video, we're going to look at exam style questions. I've got a number of exam style questions to go through. I'll produce a few videos and only do a couple of questions per video so that it doesn't become too long. So these are the first couple of questions, and at the end of the video you'll be able to click to see the next couple of questions. Okay, question 1. The Hubble Space Telescope was launched in 1990 into a circular orbit near to the Earth. It travels around the Earth once every 97 minutes. Calculate the angular speed. So we're calculating the angular speed of the Hubble Space Telescope and stating an appropriate unit. Okay, so angular speed is 2 pi over t, the time period. And in this case, t is equal to 97 minutes. And I think an appropriate unit for this would be radians per second. So I need my time period in seconds. So to convert that, I would times by 60 because there are 60 seconds for every minute. And that would be 5,820 seconds. So the angular speed would be 2 pi divided by 5,820, and that would come out as 1.08 times 10 to the minus 3 radians per second. So the first answer, 1.08 times 10 to the minus 3 radians per second. Next question says, calculate the radius of the orbit of the Hubble Space Telescope. Well, in a video to do with orbits and satellites, we looked at the force that causes things to move in that circular orbit, and that force is due to the Newton's law of gravitation. So whatever's orbiting the planet, this is the mass of the planet, this is the orbiting satellite, and that force is inversely proportional to the separation squared, the distance between the satellite and the centre of the Earth. And in this case, that is the centripetal force, so that is going to be m, and often I would go mv squared over r. However, because we've just worked out the angular speed, let's put that in terms of omega. And then it's wanting us to find the radius. So we need to rearrange this for r. I can cancel the masses either side of this equation. I can bring up r squared. I can bring down omega squared. So I'd get r cubed equals gm over omega squared. And then to find the radius, I find the cube root of that. And then just so we're aware, the gravitational constant is 6.67 times 10 to the minus 11. That's Newton meter squared per kilogram squared. M, the mass of the planet. Okay, it's not given directly in this question, so this question must rely on a data sheet that will give you the mass of the planet, and that's the mass of planet Earth. And then we obviously have the angular speed as 1.08 times 10 to the minus 3 radians per second. So if we plug all these numbers into this equation, we should get 6.67 times 10 to the minus 11 multiplied by 6 times 10 to the 24, all divided by 1.08 times 10 to the minus 3, and don't forget to square that, and then we're going to find the cube root of that, and that comes out as 6.99 times 10 to the 6 meters. Okay, so the radius of orbit for the Hubble Space Telescope is 6.99 times 10 to the power 6 meters. And then the final question, it says the mass of the Hubble Space Telescope is 1.1 times 10 to the 4 kilograms, so 11,000 kilograms. Calculate the magnitude of the centripetal force that acts on it. Okay, so centripetal force is, from Newton's second law, is the mass of the object times the centripetal acceleration. And in this case, I'm going to use omega squared r because I know omega. And so the mass of my object is 1.1 times 10 to the power 4 multiplied by 1.08 times 10 to the minus 3, sorry. And I'm going to have to square that, so don't forget to square that. If you ever make mistakes, it's often by squaring or square rooting or just missing part of the calculation. And then the radius of orbit in the last question, it was 6.99 times 10 to the power 6. When you plug all those numbers into a calculator, it comes out as 9.0 times 10 to the power 4 newtons. So 9.0 times 10 to the power 4 newtons. Okay, hopefully there was no problem following that question. Next question, number 2. This question says, a chemical centrifuge consists of 2 test tube holders which can be spun around in a horizontal circular path at very high speed, as shown. The centrifuge runs at a steady speed of 3,000 revolutions per minute and the test tube holders are horizontal. Okay, that's important to note because in a previous video I talked about an example where you do circular motion that moves vertically, and obviously it depends on if you're at the bottom or the top. At the bottom of the circle, the weight acts in the opposite direction to the centripetal force, and at the top, the weight actually acts in the direction of the centripetal force. So, because this is horizontal, we don't have to think about that. The weight's always just going to act down at any point in the rotation, so that's not going to factor in. But what might play an interesting role is the fact that the speed is given as 3,000 revolutions per minute, and what we want is we want to convert this to radians per second. Okay, so this is the angular speed. 1 revolution. Okay, so if it moves in the circle and goes around once, okay, that will sweep through an angle 360 degrees, but in radians that would be 2 pi radians. So for every revolution, 1 rev will equal 2 pi radians. We've got 3,000 of them. Okay, so if omega is 3,000 revs per minute, then we're going to do 3,000 times 2 pi to get it into radians. And then if this is in per minute, okay, for every minute that's 60 seconds. So if we divide by 60, because this is per minute, not times minutes, we're going to get it in radians per second. And if you do 3,000 times 2 pi divided by 60, that comes out as 100 pi, which is 314 radians per second. Okay, so we've calculated the angular speed in radians per second. Part B. Calculate the magnitude of the acceleration at a point on the centrifuge 95 millimeters from the axis of rotation. So this is rotating around, and if you were here at this point, which is 95 millimeters from the center, you can calculate the acceleration, because we know that the centripetal acceleration is omega squared r, and we have omega and we know r. Just bear in mind r at the moment is in millimeters, 95 millimeters, which is 95 times 10 to the minus 3 meters. So putting these numbers in, 314 squared times 95 times 10 to the minus 3, that comes out as 9.4 times 10 to the power 3 meters per second squared. Okay, so that's the centripetal acceleration. Now state the direction of the acceleration. Okay, whenever anything moves in a circle, so it will change the direction of its velocity. Okay, but for uniform circular motion, the speed won't change, so the linear speed is the same size. But to cause that change in direction, this thing must be getting accelerated towards the center. Okay, and to be accelerated towards the center, there must be a force in the same direction, and so that force is acting towards the centre. Okay, so here there's a force acting that accelerates it inwards. At this point there's a force acting towards the centre that accelerates it in that direction. So that, or the change in velocities in that direction. So the centripetal force is towards the centre of rotation. Or I suppose you could say it's inwards towards the axis of rotation, because that's the notation they gave. Okay, so at the end of the video, this will move on to a couple more questions.